We'll talk about some work in progress, hopefully to appear soon, with Mykola Dedushenko, who's in the audience, is sitting over there, and Ron Jacobi. So there are sort of two different motivations for this work, so I'll just start by describing the first one. The first one is that correlation functions of local operators are interesting observables in quantum field theory, and they're hard to compute in non-perturbative examples, and it would be very nice to have more examples where we can compute correlation functions of local operators. So in this talk, I will describe such a computation of certain half BPS local operators in 3D n = 4 quantum field theories. And so this will allow correlation functions with any number of operator insertions, but of course for a special type of operators. And the method is to place the theory on a round 3-sphere and use supersymmetric localization. Of course, this method has been used before to compute, for instance, integrated correlation functions of local operators. But in this case, there would truly be correlation functions of local operators. Okay, and to put this a little bit in perspective, let me review very briefly how supersymmetric localization is supposed to work. So one starts by choosing a supercharge Q such that Q squares to an isometry of the space plus possibly an R symmetry, and then we deform the action by a Q exact term with some coefficient T that's positive. In such a way that this term that we deform by has a positive definite bosonic part. And then we can compute Q invariant observables by noticing that if we compute this path integral where we insert the Q invariant observable in the deformed theory, where to the action we add the Q exact term, this answer is independent of this deformation parameter T. So then we can take T to infinity, and the path integral localizes to configurations where QV = 0. And one can, in this limit, the saddle point approximation becomes exact. The answer is given by the classical part and the one loop determinant of fluctuations. And using this procedure, in favorable circumstances, the path integral really simplifies dramatically. For instance, it can become, from an infinite dimensional integral, it can become a matrix model. Okay? So I want to describe, so there's a sort of a trade-off. There's a trade-off between obtaining on one hand, obtaining a simple theory after localization, for instance, a matrix model. And in order to obtain a simple theory, ideally, we would like the isometry that's part of Q squared to have no fixed points. If the isometry has some fixed points, then the fields can fluctuate wildly at those fixed points. So one has to take that into account. And there's a trade-off between this and the existence of Q invariant local operators. If there's a local operator that's Q invariant, that's also invariant to Q squared. And since Q squared contains an isometry and an R symmetry, then the operator must be inserted as at the fixed point of the isometry in Q squared. So there's a trade-off between, on one hand, we'd like the isometry to have no fixed locus, and on the other hand, if we want to compute correlation functions of local operators, we would like it to have some fixed locus so that we can put our local operators there. Okay? And just to give it away a little bit, in this talk, the isometry in Q squared is going to have a fixed locus. That's going to be a great circle on S3. So the 3-dimensional n = 4 quantum field theory will localize to a 1-dimensional theory living on this circle. And then we can have operators insertions that anywhere we want along this circle. Of course, Q invariant operators. And right, so we'd be able to calculate some correlation functions in the 3D n = 4 theory using this 1-dimensional theory. Okay. So that's sort of the first motivation. The second one might seem a little unrelated. And it's an observation made in these papers. It's sort of the lower dimensional generalization of the chiral algebra that Matt talked about. And that is that n equal 4 superconformal field theories, so in this case they have to be conformal, in 3 dimensions have 2 one-dimensional topological sectors, one associated with the Higgs branch and one associated with the Coulomb branch. By topological sector I mean that if there are certain operators that when placed on a line, their correlation functions don't depend on the relative separation of the points on the line, but they do depend on the ordering of the points on the line. Okay? And this argument follows from properties of the superconformal algebra. Okay? And let me explain in a little more detail how it works. So the n equal 4 superconformal algebra has as its subalgebra the conformal algebra SO3, 2, as well as an R symmetry, which I'll denote by SU2H and SU2C for Higgs and Coulomb. And I'll denote the SU2H fundamental indices by A, B, C, and so on, and the SU2C fundamental indices by will be dotted. It will be A dot, B dot, and C dot, and so on. Okay. This algebra would contain certain Higgs branch operators and Coulomb branch operators. So let me explain what these are. Higgs branch operators are scalar operators with a scaling dimension equal to their SU2H spin in singlets under SU2C. For example, the scalars in a hypermultiplet have this property. They have scaling dimension 1/2 and SU2H spin 1/2. There's doublet of such scalars. And Coulomb branch operators are scalar operators with a scaling dimension equal to the SU2C spin. So an example of such operators are the scalars in the vector multiplet. So the n equal 4 vector multiplet contains a triplet of scalars of scaling dimension 1. So in this case, delta equals 1 and SU2C spin is equal to 1. Okay? And then the construction of these of this 1D topological sector goes as follows. Let me describe it. So it's sort of analogous for Higgs branch and Coulomb branch. So let me just describe it for the Higgs branch, and then later on in the talk I'll focus on the Higgs branch. As I said, these operators have the scaling dimension equal to the SU2H spin, so they can be represented as SU2H tensors with 2J indices that are completely symmetric in these indices. Okay? And first, let me describe how the 1D topological sector works, and then why it works in this way. Okay? So how does it work? What are the operators whose correlation functions are topological? Well, they're what I'll call twisted Higgs branch operators. So we take these Higgs branch operators, we place them on a line, say the line parameterized by x3, and we contract their SU2H indices with position-dependent polarizations. And the position-dependent polarizations are U1 equals 1 and U2 equals x. Okay, so these indices go, they're SU2 fundamental indices, they go from 1 to 2. So essentially, when all the indices are 1, we don't multiply the operator by anything, and then when one index is 2, we multiply it by x. When 2 indices are 2, we multiply by x squared, and so on, and we add them all together. Okay, so these are the twisted Higgs branch operators. And then the claim is that the correlation functions of these operators, so for each Higgs branch operator that transforms in this spin J representation, we can have only one twisted Higgs branch operator, and the correlation functions of these Higgs branch operators are independent of the distance between the insertions, but depend on the ordering of the insertions. So this would be topological 1D theory. So to make it even a little more concrete than that, let me give an example in a free theory, a free hypermultiplet. A free hypermultiplet has scalars q and q tilde. Q tilde with an upper SU2 index is the complex conjugate of q. Indices are raised and lowered with the epsilon symbol. And so the two-point function, this is a free theory, the two-point function of q is goes like, of course, 1 over x, 1 over the difference between the coordinates, it's proportional to epsilon AB because this is the antisymmetric tensor, because this is the only SU2 invariant we can construct. Okay, so these are the operators of the 3D theory. Now we can go to the operators of the 1D sector by considering these twisted operators that I'll denote by capital Q and capital Q tilde. Capital Q is just Q1 plus X Q2, and capital Q tilde is Q1 tilde plus X Q2 tilde. And we can calculate explicitly the 2-point function of Q and Q tilde using this formula. And of course, the 2-point function is going to have this denominator, absolute value of x1 minus x2. But because of these x's here and here, it's also going to have in the numerator x1 minus x2 without the absolute value. So overall, this is going to be the sine of x1 minus x2 over 4 pi. So this is like a, this is a topological correlation function. It's independent of the distance between the operators, but it does depend on the ordering. Okay? So, so why does this work? Well, this works.
If x is supposed to be a circle, the sign has a little bit of trouble at infinity. Do we have a bunch of operators inserted so that really makes sense on the circle and include them all?
There will be antiperiodic on the circle.
Oh.
So why does this work? It works because as part of the superconformal algebra, we can find a supercharge that I'll call QH. There exists, in fact, a one-parameter family of supercharges that are linear combinations of two nilpotent supercharges, but that's not very important, in such a way that these twisted operators O of x are invariant under QH, and the translations of these operators, the twisted translations of these operators, are QH exact. And these two properties imply that the correlation functions of these operators O of x are topological. I should point out that as in Matt's example with the Carrel algebra, that QH is a linear combination of a Poincare and a superconformal supercharge. So it's it seems that superconformal symmetry is important for this construction. Okay? And in the rest of the talk, I will actually obtain an action for theories with Lagrangian descriptions, an action for this 1D topological theory. Okay? So what is the method? The method is to map the theory to the 3-sphere and localize with respect to QH. And QH squares to a rotation around the x3 axis and an R symmetry transformation. So indeed, the isometry that Q squares to fixes this line, or the line after it's mapped to the sphere, the line becomes a circle. So upon the stereographic projection, this x3 axis where the operators are inserted becomes a great circle parameterized by a coordinate phi. Okay? So the topological theory is gonna live on this circle, and we're going to be able to insert any number of these twisted Higgs branch operators at various points on this circle. Okay? I'll describe a few of the steps in the supersymmetric localization computation. Okay? So there are a few observations. The first observation is essentially a group theory observation, which is that after the stereographic projection, this supercharge QH, which is of course part of the superconformal algebra, is also part of a smaller subalgebra, which is a massive n equal 4 algebra. It describes theories on the 3-sphere that are not conformal, but they have n equal 4 supersymmetry. So this massive n equal 4 algebra is SU2/1 times SU2/1. It's a subalgebra OSP44. And it contains, as its generators, the isometries of S3. There's an SU2 here and an SU2 here. That's the isometry of S3. It contains a U1 squared R symmetry. There's a U1 here and a U1 here. And it has H supercharges. There are 4 here and 4 here, as appropriate for n equal 4 supersymmetry. So the conclusion is that the one-dimensional theory, topological theory construction that I reviewed before, does not require a superconformal field theory. We can study more generally just n equal 4 quantum field theories on S3 that are invariant under this superalgebra.
Sorry, what is this superalgebra?
SU2/1 times
No,
SU2/1.
but why do you call it massive n equals 4? What does that mean?
Oh, because it doesn't contain any conformal generators. Massive stands for non-conformal. I should have called it non-conformal. It's just the n equal 4 it's just non-conformal n equal 4 algebra.
So can you,
Yes.
for those of us who might be forgetful, can you remind us of examples of theories with this symmetry?
I'll give examples in a bit.
Okay.
Okay. So the examples are coming right here. We can construct actions. You should think of quiver gauge theories built from vector multiplets and hypermultiplets, and you can think of the action as having a Yang-Mills term and a kinetic term for the hypermultiplet. Okay, so it's possible to construct a curved space version of the Yang-Mills action that's invariant under this action, that in the limit where the radius of the sphere goes to infinity becomes the usual Yang-Mills action. And the kinetic term for the hypermultiplet, you just add the conformal coupling to put the theory on the sphere. That's right. I'm not going to be considering that here, but I think in principle that should be possible. You can also add twisted hypers and twisted vectors, but for simplicity, let me just restrict to theories built from vector multiplets and hypermultiplets, and these generalizations are of course possible. Okay? And the second observation is actually a hard calculation that shows that the Yang-Mills action is actually Q-exact. The fact that the Yang-Mills action is Q-exact, it was known before that the Yang-Mills action is Q-exact with respect to a supercharge that's contained in an n equal 2 superalgebra, but QH is not such a supercharge, so actually we had to do a calculation to show that this is true. So there are two consequences of this fact. The first consequence is that the S3 partition function and the correlation functions of these QH invariant observables are independent of G Yang-Mills. And the second consequence is that we can take G Yang-Mills to 0, or in other words, we can localize the vector multiplet by adding the Yang-Mills action with a very large coefficient. If we do that, the vector multiplet fields localize to 0 except for one scalar in the vector multiplet that localizes to a constant function on the sphere, which I'll denote by sigma. The situation is the same as in previous supersymmetric localization computations, for instance those of Kapustin, Willett, and Yakov, but those use a different supercharge. That supercharge belongs to an n equal 2 subalgebra, meaning it belongs to only one of these SU2/1 factors in SU2/1 times SU2/1. This Higgs-Brand supercharge does not belong to only one factor. It's a linear combination of supercharges in both. Okay? So after the vector multiplet localization, the partition function takes the following form. So of course we can diagonalize sigma by a gauge transformation. So it's an integral over the Cartan of the gauge group. There's a determinant coming from fluctuations of the vector multiplet fields, and then we have the remaining hypermultiplet action, which is just three-dimensional action. But the observation is that for fixed sigma, the hypermultiplet action is actually quadratic. So at fixed sigma, we can compute correlation functions in this theory of the hypermultiplet coupled to sigma by just performing Wick contractions. Of course, not every correlation function that we compute using this theory will agree with a correlation function in the superconformal field theory. It's only those that are invariant under QH, of operators that are invariant under QH, that we can compute this way. Okay? So in some sense, we're actually done. I can just use this formula to calculate correlation functions of these twisted Higgs branch operators. Okay? But of course, we can go one step further and try to do the hypermultiplet localization as well. As I said, we don't need to do this because we can already compute everything that we want from what I showed you so far. But we can try to add a localizing term for the hypermultiplet and see what the theory localizes to. And this is a long computation, and it's interesting in its own right, and I'm not gonna explain it here, but I'll just tell you what the answer is. The answer is the following. So the partition function is an integral over the Cartan of the gauge group. There's again this determinant coming from the vector multiplet fluctuations, and that for each hypermultiplet, we have a one-dimensional partition function over some fields q and q tilde. These fields q and q tilde are precisely the twisted Higgs branch operators when mapped to the sphere. So q is cosine phi over 2q1 plus sine phi over 2q2, and same for q tilde. They are anti-periodic, to answer Edward's question. And the action that we get looks like q tilde dq d phi plus q tilde sigma q. Okay? And the constant that appears up front is related to the radius of the sphere. So after all this localization procedure, what we get is a one-dimensional Gaussian theory coupled to a matrix model. So extremely simple. We can now use this theory to calculate correlation functions of these q's and q tildes, or operators built out of q and q tilde. Let me try to make contact with the results in the literature, namely with the Kapustin-Willett-Yakov matrix model. So localizing with respect to the Kapustin-Willett-Yakov matrix model, one obtains a S3 partition function that looks like this. So there's the vector multiplet determinant, and for each hyper there's a 1 over determinant of this Koch function. So what the result that I showed you before does is essentially expanding the determinant for the hypermultiplet into a one-dimensional Gaussian theory. Okay? The benefit of this, of course, is that we can now insert any number of q's and q tildes and compute their correlation functions using this expanded form. And we did many such calculations. We produced all the known results about these operators in the literature and more. And I just wanted to show you one example. The example is a necklace quiver. So the gauge group is U1 to the n mod U1. They're n U1 gauge groups and bifundamental hypermultiplets. Here I just denoted by q and q tilde the twisted Higgs branch operators. Of course, these are linear combinations of the hypermultiplet scalars, the little q's. And nothing is charged under the overall U1, so we mod out by the overall U1. And in this theory, the twisted Higgs branch operators are, they have to be gauge invariant, so there are only very few possibilities of constructing gauge invariant operators. We can multiply all the q's together, so I'll call that x. We can multiply all the q tildes together, I'll call that y. And we can go back and forth between two nodes, so that would be q1 tilde. And by the d-term relations, q1 tilde is equal to q2 tilde, and so on, and I'll denote that by z. Okay? And the most general Higgs branch operators are just products of x, y, and z. Okay? So just to be explicit,